Can you hear me? No. Can you hear me now? Do I need to raise it? Can you hear me now? Okay, perfect. I'm in front of the screen. Okay. Okay, thanks. Thank you, Matt. Thank you to everyone for coming on this rather gloomy evening. Let's see if we can make this fascinating. So I'm going to be talking to you today about some complex and fascinating objects. I already learned something, that scientists are like black holes, both of them are complex and fascinating. And I hope I'll convince you of why they're interesting. The title I chose was Binging on Black Holes. The reason for that will become clear during the talk. But before I begin, I wanted to bring out a poem that I really like, which describes what we do as astronomers. At least I think it does. This was written by one of my former supervisors, who unfortunately passed away at a very young age of only 39. But she describes herself and astronomers as nomads. We astronomers are nomads, merchants, circus people. All the earth our tent. We are industrious. We breed enthusiasms. Honor our responsibility to all. I really like that. I think it describes me very well in many respects. I'm from a very different place. I've worked all around the world, and I feel sometimes my life really is like a nomad. And I also really like this phrase, honor our responsibility to all. I think that's one of the fundamental aspects of astronomy which really reaches out to everyone. Who amongst you didn't want to be an astronaut or travel into space when you were young, at least? And I hope I will be able to awe you at least a bit today. Okay, so moving on. At the end of this talk, I hope you will be able to answer all these questions. What are black holes? What powers them? And why do we care about them? Why are they interesting to begin with? Okay. So let's start with the obvious. What is a black hole? Who knows? Anyone? Shout out the answer. Go ahead. Well, black holes can be shy too. I'll come back to that later. Anyone at all? Dead stars, yes. Anyone else?
Things that suck up other things.
Okay. Not too bad, yes. Yeah. My mouth too. Yes. Okay, so one of the definitions, if you want, is that there are point masses of infinite density enclosed by an event horizon, causally disconnected from the rest of the universe. In other words, giant, big suckers, if you want. This picture, many of you may be aware of this picture, you've probably seen it. How many of you have seen this photograph? So our lives as black hole scientists have become a lot easier after this movie came out, Interstellar. If you haven't seen it, I do recommend it actually. It's got some interesting science in there, and some of these depictions are quite realistic. In my talk, I will be concentrating exclusively on what happens outside the event horizon. Okay, this is the event horizon. Once you fall beyond this location, beyond this radius, there is no escape. Basically, you are pulled irretrievably downwards to the center. Okay. If you want to know what happens inside the event horizon, then please wait until. So I'll be staying firmly outside the event horizon in my talk. But if you want to know what happens once you cross that horizon, please wait until the next talk. Okay? Then Marika can enlighten you. Okay. Now, how do we find them? Well, this is one of the deepest images of the sky that we've ever taken. It's only a small bit of sky, no larger than perhaps the fingernail on my thumb when I hold it out to that extent. It's just a small bit of sky. But every single point of light here is a galaxy, an entire galaxy with its own billions of stars, like our Milky Way, and trillions of solar systems, perhaps, and Earths, who knows. Okay? So many of you may have also seen this picture before. But I'm guessing that not many of you have seen this picture, which is one of the deepest images we have of black holes. Okay? So every single point of light here now is a black hole. It's a supermassive black hole, actually. Okay? So these supermassive black holes are also spread throughout the universe. Basically, we now think that every large galaxy has a supermassive black hole at its core. Not all of them are shining all the time, not all of them are bright, but every large galaxy does have black holes at its core. The different colors here just tell you, well, I'll come to that later on, but they tell you about what is it that's making these black holes shine. I'll come to that later. Okay? This image was taken by a satellite called Chandra. It's an X-ray satellite which detects X-rays from space, instead, as opposed to what our eyes can see, visible light. Chandra is actually named after an Indian scientist, one of my heroes, who he predicted the existence of black holes before they were found. And he did this on a boat trip over from India to Cambridge when he was only 19. So there's still time for you young ones out there. Make good discoveries. Okay. Oh yes, I wanted to point out that, so this is an X-ray image in the background. If you were to zoom in on any one of these black holes, this is what you'd see, an entire galaxy, okay? And perhaps at the center there'd be a very bright shining object, almost as bright as the rest of the entire galaxy. Okay, and that is a growing supermassive black hole. Let's zoom in further on these objects, on the black holes themselves. So what do they look like? This is an artist's impression. We don't have a picture yet, an actual photograph taken of a black hole. We might do in another year or so, actually. But as for the moment, we have to do with these artist's impressions. So this is what a black hole may look like when you get up close. Okay? What are the different bits to this? Well, there's the black hole at the center. Okay? There's all this swirling mass around it. The swirling mass is called the accretion disk. It's basically stuff that's being sucked in, as we heard. And as stuff is sucked towards the black hole because of its strong gravitational pull, comes in, it forms a accretion disk, and matter slowly, gradually swirls into the black hole. There's also this other bit, what we call a jet of outflowing material. It's not actually coming out of the black hole, because once you cross the event horizon, you cannot escape. It's actually stuff that couldn't quite accrete onto the black hole. It was just happened to be shot out, came in too quickly, basically. It had to be shot out. Some of it was shot out instead of falling down through the black hole. This is what we think black holes look like. Okay? But if you remember at the beginning, I showed you this image. Okay? So what is the difference between this image and this image? How are they different? Well, this is definitely an artist's impression. Okay? This is also an artist's impression, but this is based upon a more realistic simulation. Okay? Even though it doesn't have a jet, that's the one aspect which is missing, which is why I wanted to show both. But this also illustrates an interesting effect. So does anyone know why these two look different?
Is it the light bending around?
Very good. That's exactly right. Yeah. Basically what happens is that the gravitational pull of the black hole itself is so strong that light from the back of the black hole, from the accretion disk at back, is actually sucked forward, sucked towards the black hole, and it basically it appears as if it's appearing from above the black hole. You see what I mean? It forms this ring around the black hole. Now, how many of you have wine glasses in front of you? Empty wine glasses, I should say. Excellent. So you can actually create your own black hole if you want. Okay? All you need to do is hold up the wine glass towards a bright point of light. Okay? And just move it around a bit. You should be able to see the light turning into a ring. You see that? Yeah? And this is happening because the light rays pass through the glass in particular ways. Effectively, the net effect that you get is that light is bent. And the mathematics of these wine glasses is similar to what we see around these black holes, in very simple terms. Okay? So, wine glasses are great. Okay, so yes, this is exactly light bending. Okay, so this is nice. This is very center of these, around these black holes. Where does all this material come from? That's swirling in onto the black hole. It can't just appear out of nowhere. It must be coming from somewhere. Well, it comes from the large-scale galaxy, right? And it turns out that most of these growing supermassive black holes are shy, as I mentioned before. And I say that because it turns out that a lot of them are embedded in a large lump of gas and dust, what we tend to call a donut or a torus of some kind. And this is matter that's swirling in from the larger galaxy and then accumulates onto the, close to the black hole, and then eventually feeds the accretion disk, and it finally falls down through the black hole. Okay? So growing black holes tend to be shy. In fact, most of them are this way. So you use special techniques to prod them out of their shyness. Putting it all together, just to give you a summary, if you want to study these black holes, on the largest scale, this is what we're looking at. We're seeing billions of black holes spread throughout the universe. Okay? If you zoom in on any one of them, you see entire galaxies, and at the core there is a black hole, perhaps embedded in gas and dust. And if you zoom in even further, then you tend to see accretion disks, matter swirling in, and these jets. Again, this is just an artist's impression. We don't have this picture yet. And the scales here, you can see, you go from basically hundreds of millions of light years or more down to just light days. If you think about it, matter has to travel. It's an enormous journey which matter has to take to actually fall down into the black hole. Okay. I said before that some of these black holes can be bright enough to outshine entire galaxies. How can they do that? Well, let's first look at the light coming from these black holes. They're really quite crazy in many respects. So this is what we call a spectrum. Basically tells you how much light is coming out of these black holes at any given wavelength, any given energy of light. Okay, so you have radio waves over there, infrared, visible, UV, and X-rays. So for comparison, I'm going to put up what the spectrum of the sun looks like. Does anyone know where the spectrum of the sun peaks? Where does the sun give out most of its light? In which Whittleby bands? It's not there. Okay. As opposed to this, what do black holes look like? Any guesses from the non-academics? Yeah, very good. X-rays, I already mentioned that. Yeah. Actually, it turns out that they're bright across the entire electromagnetic spectrum. Okay? So they're bright in X-ray, they're super bright in UV, they're bright in infrared, and they're also pretty bright in the radio. Okay? So you can study them at pretty much any wavelength. In fact, we need all these wavelengths together, the light from the entire electromagnetic spectrum, in order to understand the full physics of what's happening. Okay? This is just a comparison in how these shapes look, but actually some of these supermassive black holes I told you are incredibly bright. So if you were to put them on a proper scale, the sun would lie way, way down there, much, much weaker. These black holes tend to be as bright as 10 billion suns. Okay? So that's pretty. And this is just a typical black hole that we find. It's not super special in any way. So how can they emit so much light? Well, it all comes down to the beauty of accretion. Now, if I remember correctly, what comes next? Yes. So there's only one equation in my talk, okay? And hopefully it's not a scary equation. I think you've all heard about this one before. E equals mc squared. Anyone want me to explain it? Well, anyone want me to describe it in a bit more detail? Okay. Tells you how much energy can be emitted if you were to convert matter, take the energy of matter and just convert it into energy, photons, for example. So if you were to take a lump of material and just, if you were able to extract all its energy, the amount of light that you would see would be given by this equation. It's how much potential there is, if you want, in that mass. And so this is the equation we use, essentially, to work out how much light we are seeing, or how bright these black holes are. basically what's happening in these systems is that you have matter going in, okay, swirling in through the accretion disk, okay, and effectively what comes out is light, this energy, okay. So what we can do is, well, we can observe this energy because we have telescopes which can just see the light, okay. So we can observe this energy, we know this equation, so we can work out the mass that must be going into the black hole, okay. How much mass are these black holes actually sucking up to power this incredible amount of light, equivalent to 10 billion suns? Well, turns out if you work out the numbers, and I did this very quickly, for assuming that a typical black hole is giving out about 10 billion suns, equivalent of light, and it's actually sucking up 1,000 Earths every single year, roughly speaking. Okay? So I'm sure you're glad you don't live in the immediate vicinity of a black hole. Okay? So that's pretty incredible. But it's in one respect, it's pretty basic physics. It's nothing. We think we roughly understand the physics of what's going on here, not in detail, and we think magnetic fields are involved, okay, but I'm not going to go into any more detail. Okay, what happens to all this energy that as it comes out? Where does it go? Well, it goes out into the light that we see, of course, as I showed you, but also it can have other very dramatic impacts. And I'm going to show you a movie now of what we think could be happening. So this actually shows the merger of two big galaxies and the formation of a very large black hole at the center. I haven't talked about how these black holes form, and in fact we don't really understand how they form, but this is one possible mechanism of how they grow at least. So two big galaxies come together, like our Milky Way and Andromeda, for instance. Over billions of years they get closer and closer, and I want you to notice this blowout of what's happening when they get closer together. What's happening is that a lot of gas gets concentrated down to the core, to the nucleus. That accumulates onto the black hole. The black hole becomes so energetic that it can actually blow away all the material around it. You want me to play that again? Okay, I think this is So the time scales at the top are in millions of years. This is very quick in cosmological scales. This is a realistic simulation of how we think two galaxies interact. The interaction tends to produce tides, tidal forces, which force material down to the center of these systems. Black holes at the center accumulate a lot of energy. Basically, they start to grow. They give out a lot of energy, as we saw before, and that energy is what we see coming out here. It becomes powerful enough to actually disrupt the entire galaxy. Okay? So they suck up material, but when they're growing, they can also blow out a lot of material. Okay? This is a simulation, of course, but is there any direct evidence for this? And the answer, of course, is yes. There's many different bits of evidence I can show you. This is just one of them. This is our own Milky Way galaxy. This is the plane of our galaxy. Well, this is the perspective of the Milky Way as we see it. Basically, it's the full sky image. If you could take the full sky image, and the black hole the black hole in our galaxy sits right at the core, at the center there. And what you see is this faint, fuzzy blobs on either side of the galaxy. These are giant big bubbles which we believe have been blown out by the black hole at the center of our own galaxy. I'll come back to that later on. But this is evidence of past activity. At the moment, the black hole at the center of our galaxy is actually pretty dim. It's not growing rapidly, it's bubbling along. But perhaps tens of millions of years ago, it was actually incredibly bright. It would have been one of the brightest objects in the near infrared in the sky after the sun. Right? Okay, and it could well become bright again. Who knows? In fact, there were predictions that it was supposed to happen this year, but it didn't. Could well become bright again. Okay, now I want to ask you a question. Given everything you've just heard, what if there were no supermassive black holes in galaxies? Or what would be the effect on galaxies, given everything I've just told you? They will be destroyed or they won't be destroyed? Well, they won't. That's the key. So what I showed you before was that as they're growing, they can actually give off all this light and winds, we call them, and a lot of energy comes out of it. But effectively, if you cut off that supply, and there's very little to stop galaxies from just growing and growing and growing forever. Well, not forever, but they can grow much, much larger than what they would otherwise. So this is how our Milky Way might actually look if it weren't for our the Milky Way, the black hole at the center of the Milky Way. This particular galaxy appears to be much, much larger than other galaxies in the field. This is because it sits in a cluster. So it's not a fair comparison, but it's just to give you an idea of how our Milky Way might have been. It could have been much, much bigger than otherwise. It could have been even more stars in the sky. Okay. Okay. I wanted to talk just briefly about two other things. So I talked about how black holes can be powered, but I didn't really tell you in detail about what's happening in this case. So basically, we have material which is actually being sucked towards the center, and that somehow is extracting energy. Okay? Now, again, the details of that, how that happens, I won't go into those details. The magnetic fields are involved, yes. But I did want to just give you a rough intuitive idea. And all that's happening basically is how we are extracting the potential energy, the gravitational potential energy of the material. What does that mean? It just means that if you drop something, you can, it does some work, it gives off a sound, yeah. All that energy is converted, gravitational potential energy is converted into sound energy, into just the motion bouncing back, etc. But if I were to drop this from much higher up, say, okay, yeah, well, you can't really say it, you can see it there, but the energy given off is much larger, right? Okay, it has much more potential energy, so much more is given off from that. And that's what happens in these accretion disks, because they're falling in this strong gravity. The closer you are to the black hole, the more energy is given off. See what I mean? Okay? Because you're getting deeper into the potential level. So, what happens is, if you were to ask yourself, where is most of the energy given off? It's actually right in the core. Okay? And we think that if you actually were to ask yourself, as a function of radius, just distance from the black hole, how much energy or heat is coming out, if you want, and it would look something like that. Be very, very hot in the center and cooler outside. Okay? In fact, the difference is so strong that in the center we probably have something like tens of millions of degrees or even larger. Gas, which is incredibly hot. In the outskirts we have cool gas at only 10,000 degrees, which is still pretty hot for us. But the difference is that this is so hot that it gives off copious amounts of X-rays. And here you see light in the optical and the ultraviolet. Okay? So this is why you see that broadband spectrum, if you remember, which is much, much broader than the sun. Okay? This is where a lot of the energy comes out. And just want to emphasize that we can learn something new at every single wavelength that we study. So this is just an example of a galaxy. In fact, oh yes, there you go. The Whirlpool galaxy. It's a nice big whirlpool. Seen at X-ray light, UV light, optical, infrared, radio, and you can see that the structure looks different at every wavelength, doesn't it? And that's because in X-rays, for instance, you're looking at the hottest stars and supermassive black hole emission in the core. This one has a very, very bright but obscure supermassive black hole. In the UV, you're seeing very young stars which are just being born. In the optical, you're seeing light that our eyes can see, for instance, typical stars like the sun. In the infrared, it turns out to be dust. And in the radio, it's a complex mix of processes, including new stars and hot plasma, etc. So you do need all these wavelengths to understand the full physics, because if you just concentrate on one wavelength, for instance, it's very difficult to actually separate out. Very good. Okay. Do I get a permission? yeah, so this is how you can explain all these images, basically, because you can study them in X-rays, but at the same time, if you study them in the optical, you learn something completely different. That's what I wanted to emphasize. The final bit that I wanted to talk about is how we actually study these objects, because I've been throwing out all these numbers that you've got, supermassive black holes and incredibly powerful. But how do we know this? How do we know that they are supermassive, really? Well, the best example we have, where we've really been able to measure the mass of a black hole, actually weigh a black hole, is the black hole at the center of our galaxy, our own galaxy, Milky Way. This is just, that arrow is supposed to be 1 light year long, so, and we are located about 30,000 light years away from the center, away from this region, basically. So you're really looking at the very core of our galaxy. And what we then do is to just try and map out. The black hole itself is weak, it's faint, we don't see it, okay? But we can work out its mass using simple gravity. Okay? Just like satellites going around the Earth, all we do is we map the motions of these stars, and then we can work out how much mass must be in the black hole. And that's what has been done. So this is the center of our galaxy. These are stars going around the center of our galaxy. And what has been done over many, many years is to work out these orbits of how quickly these stars are traveling, what is their center of mass, basically what are they going around. And by doing all these calculations, it's quite painstaking work, it's been worked out that all these stars are being pulled. The reason that they're going around this cross, and by the way, there's no big giant cross in the sky, that's just to guide your eye, unfortunately. That would be really nice to have that cross. And it's been worked out that at that point, basically, which is dark, there must be a mass equivalent to 4 million suns, all contained in a region of space perhaps more larger than our solar system. Okay, so imagine our solar system filled with 4 million suns worth of mass. That's pretty incredible, isn't it? And that's just a limit. We think it's actually contained in a much, much smaller region. In fact, infinitely dense region. Okay, so this is the best evidence we have of a supermassive black hole, and this is how we measure their masses if we can. Okay, final slide is just a comparison, because it's, again, it's very difficult to imagine what these numbers mean, 4 million solar masses, etc. So I did a quick comparison. This is the supermassive black hole that I showed you before, say at the center of our galaxy. This is what the sun looks like. So the comparison here is about 4 million. Okay, that's my little monster. She weighs about 10 kilograms, 13 kilograms. Okay. So I was trying to think of a relative comparison. What is she in relation to, in the same size ratio as the supermassive black hole at the center of our Milky Way is to the sun? And it turns out, and I searched for various things, but it turns out that she is 4 million times more massive than a mosquito. Okay, which I thought was interesting, but it didn't quite convey the sense of what I wanted to say of really how incredible that is. Well, since we are in a pub, it turned out, when I did some calculations, that the mass ratio, or a mosquito basically, is equivalent in mass to a few thousand bubbles of water or beer. Okay? So actually, just this foam head, a thin foam head, is what we're talking about here. That's the mass ratio in terms of relative comparison. And on that note, I'm going to finish. Wish you cheers. And I hope what you've learned is that black holes are really present throughout the universe. Complex and fascinating objects, as we learned. How are they powered? It's accretion of matter onto these black holes that really powers them. And we need multicolor eyes. We need information from all these different parts of the electromagnetic spectrum to study them. If you don't have all that information, then you miss out on some bits. Thank you very much.
Thank you very much, Poshak, for that wonderful talk. There's a very evocative image at the end. I love how you definitely found something everyone in the room can relate to with the foam on the beer.
I had to try hard.
It felt very natural. So I'm sure there's plenty of questions to Poshak after such a great talk. Would anyone like to ask anything? Have they got a burning question in their mind after that?
Don't be shy.
Yeah, we've got one over there.
So how's light affected by black holes? Like in the movies that you see absorbed by black holes, is that happening? Like,
oh yes, absolutely. This I told you about this light bending effect.
yeah.
We think that when you get close enough to a black hole is just like a giant vacuum cleaner from which nothing can escape, not even light. And basically, what it does is basically curves. We say it curves space-time around it, and light tends to follow that curvature. So it's happening all the time, and that's what creates these interesting, strange effects of the rings around the black hole and in the wine glass. Yeah. In fact, it's an unsolved problem. How much light is actually falling into the black hole when these things are growing versus how much is coming out? It could be that we're actually missing a large fraction of the brightness of the black hole because it just gets sucked in instead of coming towards us.
Okay, thank you. Have we got any more questions? Yes, over by the exit there. We've got a microphone that will come to you. Continue it.
Hello, yes, great talk, thank you very much. What happens to dark matter when it reaches a black hole?
That's a good question.
Sorry.
So the short answer is I do not know. I haven't thought about it in detail. The long answer is that it depends upon how strongly dark matter interacts with other dark matter, for one. Okay? We think that dark matter is primarily makes itself known, its influence known by gravity. Okay, that's how its influence is felt. So in principle, it should get sucked in to the black hole like any other matter, in principle. Okay? But the densities of dark matter around these black holes can be so high that you can actually have dark matter particles interacting with each other and annihilating, and you can get even brighter bursts of radiation because of that. But the details of that would depend upon the exact environment. Yeah, at least we got that.
Oh, another pointer. I think we've got 2 or 3 in that talk, so if you have got a filled bingo sheet, do bring it down. We've got quite a few questions now that have been sparked off by that, if we can get the microphone in there to some of those. I think we might take one more and then go to the break, but I'm sure Poshak would be willing to answer questions at the bar. And there's always the wonderful shiny tombola if all else fails.
Are the black holes actually moving in any direction?
Sorry, where are you? Yes, hi.
Are the black holes actually moving in any direction in space?
Yeah, that's a great question. So, yes, in principle, yes, they're free objects, freely floating objects, potentially. They are attracted to other massive objects, and so they're just influenced by gravity like any other object. For example, our own galaxy and Andromeda are moving towards each other and will collide in about 5 billion years. Okay? And so the black holes at the center of the particle galaxies are also moving in the same direction, if you know what I mean. Okay? Even within our own galaxy, there's millions of many smaller black holes which rotate along with the rest of the stars. So it's just the gravitational influence and their initial direction of movement which governs how they move. Yeah.
Thanks very much. I'm really sorry to cut it off there, but as I say, I'm sure there'll be more conversations over a pint or 2 at the bar. And yeah, we need to have a little bit of time for everybody to get those pints in. But you mind just swapping over the projectors there? So, in fact, yeah, we are going to have a short break now for about 10 minutes.